class. Okay, so good morning, everybody. We will now be discussing wide area networking today. So this is again, as I mentioned a while ago, it's basically a network that covers a relatively broad geographical area. So normally, between, for example, it can be considered between buildings in a city, for example, or a whole country, or the whole world, for example. So the internet is an example of one of the largest wide area networks, right? So which we call as WAN, right? So it is normally a collection of multiple LANs, right? So LANs are basically local area networkings. They are normal local area networks that they cover a particular administrative domain. So for example, certain organizations like the Ateneo de Manila University, whose entire campus would be covered as a wide area network. However, once you cover the different Ateneo de Manila University campuses, they are now considered wide area. The key differentiator is often the use of public networks in the middle. So for example, the Ateneo de Manila Loyola campus is connected to the Ateneo de Manila Ortigas and Rockwell campuses via something called a wide area network connection, or a public network, which basically is provided by a telecoms provider. In our case, like a PLDT, a Globe, or a Converge, for example, are examples of telecommunication providers that run what we call public networks. These networks, so wide area network providers, are public because anybody can subscribe to their service, and the network is used as a shared service amongst different entities, hence the term public networks. The goal for today is basically to determine the proper parameters when selecting various wide area networking technologies. So if you put yourself in the position of a telecommunications provider, or in the position of an enterprise picking a telecommunications provider, because these telecommunications providers will generally provide multiple wide area networking technologies for your choice. So again, this is still a exercise in connecting various networks together. Right? So first off, what is a WAN, right? So it can be privately owned or rented, right? So the thing about public networks is you can rent, right? You can rent capacity from PLDT or Globe. When we subscribe to the internet, for example, we are subscribing to a public network, so that's rented, right? It's a shared user network, and you can lease facilities from what we call common carriers or telecommunications companies. There's another term called metropolitan area network, or MAN, which is like an intermediate form of WAN that is tied by a geography. Say you're within the same city, sometimes you would call it a metropolitan area network. And of course, as I mentioned just a while ago, the internet is an example of one of the largest wide area networks, being composed of many, many public telecommunications companies and shared networks. Right. When we talk about wide area networks, we talk about the lower three layers of the OSI stack. Now, the higher layers are normally IP, and its ilk are basically the protocols that we will be using. But WAN protocols generally span the lower three layers, right? So that's the physical, data link, and network layers. Okay, and that will be the focus of our discussion today and next week. Issues that wide area networking tends to solve is that if we move towards more distributing processing architecture, which is the norm today. For example, when you access the internet, when you check your email, when you access Gmail or Facebook, these are what we call systems with distributed architecture. They are far away from you, right? You are using it at your home, but the Google servers can be, say, in Hong Kong or in Singapore or in the States or in Pasig, for example. So they'll be in different places. But when you access them, it's just Facebook or Google, for example. So these are distributed architectures. The system is distributed in many locations around the world. Multiple applications are now being hosted centrally. So you don't have to have a copy of Facebook in your computer to use Facebook, right? It is quote unquote cloud hosted, right? So the prevalence of cloud computing has made wide area networking important. In this day and age, for work from home, school from home, you are using your wide area networks or your retail internet connectivity, which is a form of subscription to a wide area network, to access technologies such as email, social media, and the like, and learning management system. Like, for example, now we are connected to Canvas, for example, or Zoom, but these aren't hosted inside the Ateneo premise, or they aren't hosted by yourselves in your homes. Right? So wide area network technology has allowed to expand networks, so we can connect to multiple networks. When we talk about wide area networking technology, so before we go into the specifics of wide area technology and discussing the various types of wide area technology, wide area networking technologies, we want to look at what are the things we need to consider when picking a technology. So number one is the nature of traffic, right? Not all internet traffic are created equal. Some are streaming, watching a movie, listening to this Zoom call, for example, it's what we call streaming. But when you check social media, read and reply to your email, this is what we call bursty traffic, right? So again, different types of traffic render well to different types of circuits. So for example, streaming traffic tends to do better in dedicated service, right? They don't necessarily need a lot of bandwidth, but they do need a lot of, they need to do consistent bandwidth, and the latency must be at a certain level. So dedicated circuits work well. In last week's discussion, this could mean a circuit switch network or a virtual circuit within a packet switch network. While some traffic could be bursty, right? Checking email, checking your social media, right? Accessing a website, these are what we call bursty traffic. And bursty traffic renders well to packet switching networks because you don't need to use capacity at a consistent performance level, but you may need to access a lot of data at certain times of the transaction. So nature of traffic matters, and these are examples of that. The second one is strategic growth and control. How much do you need now, and how much do you need in the future? Many wide area network technologies have a limit. So for example, if you need 1 gig now, but you need 2 gigs in the future, you need to be able to subscribe to a circuit that allows you to upgrade to 2 gigs later. So for example, if you use dial-up telephone technology at 56 kilobits per second, you may need 56 kilobits per second today, but the moment you need to use 100 megabits per second, then you have to change the technology, right? You can't use dial-up anymore. That's the reason why you need to forecast your growth and you need to plan it, and you have to pick the proper wide area networking technology to ensure you can do that growth. The third is reliability and performance, right? WAN has advantages over public networks like the internet because then you can subscribe to many types of technologies from many providers. That being said, you can also use multiple providers, right? If one is as reliable, two is reliable, but putting two together makes it even more reliable. So reliability and performance is important. Again, not all WAN technologies are created equal. Fourth is security, right? Not all networks, again, have a focus on security. Some are just treated as transport networks and their security is dependent on you. Some are transport networks that are shared. Some are transport networks that are dedicated. So when they say the circuit is dedicated, then generally you can rest assured that no other user will be seeing your traffic. However, in the scenario of a shared network, other users would be seeing your traffic, and that's the reason why you normally have to add an additional layer of security. Right? So that's a security matters. Right? Not all networks have security baked in, and some networks are actually shared. So there will be multiple users in that network. Next is cost. Right? So certain networks are cheaper, certain networks are expensive. However, there is a general trend today that LAN technologies are being used for wide area networking technologies, and that's the reason why wide area networking technologies are also becoming cheaper. LAN technologies tend to have high bandwidth and are cheaper because they're only in a small geographical area, or they move or sell volumes that are much larger. But as WAN technologies mature, some of them are being used for wide area, and that is the reason why costs are going down in general. And last but not the least, we have to pay attention to disruptive technologies, right? In the last few years, for example, in the last 5 years, gigabit passive optical networks, or GPON, have become popular. That's an example of disruptive technology. And that's the reason why you will see in the last 5 years the really big growth in terms of fiber to the home technology, because GPON has made fiber and therefore high bandwidth internet at the last mile cheaper. But who knows what would disrupt the GPON technology in the future? Would it still stay predominant, or will another technology overtake it? We do not know, and that's the reason why we must pay attention. Okay, so first off, this is just a comment on wide area networks for voice. So wide area networks for voice have to be reliable. So non-variable delay, in general, a latency of less than 100 milliseconds is required for voice. It's traditionally difficult to do this in terms of packet switching. That's the reason why circuit switch networks, voice networks tend to be circuit switch. Now, of course, in the move towards more packet switch networks in the wide area networking space, some people resort to creating virtual circuits to provide this reliability. In some cases, you just have a lot more bandwidth, right? Of course, there's also this movement towards software-defined wide area networks, which allow you to use 2 or 3 multiple wide area providers to provide the reliability of a circuit switch network. So that's one of those, disruptive trends that are hitting the market right now, the software-defined networking trend, which has brought us the software-defined wide area networking technology, which we will discuss, don't worry, later. Next, wide area networks for data. Now, the nice thing about wide area networks for data is there's a lot more, because again, a lot of networking technology really is designed for data. And here are some examples. For example, in public packet switch networks, so these are packet switch networks that are public in nature. Frame relay was the most popular one before it became popular. Banks like to use it, although it has become obsolete already, but that used to be the most predominant. Then the next one is AETM, or asynchronous transfer mode, right? Which takes advantage of underlying adaptable SONET networks, which are still evolving up to today. Lease lines between sites are also another option. You can get a dedicated circuit between sites from a telecommunications provider. So a telecommunications provider can even put a circuit, say a fiber optic circuit between your 2 sites. That's what we call a dark fiber, right? So it is provided you unlit. It's just a fiber, it's just a cable, and it's leased to you. So that's dark fiber. However, most lease lines by telecommunications providers are actually lit, and they're actually part of shared networks like ATM or frame relay, but they're encapsulated in a virtual circuit, hence they can be sold as a leased line. And last but not the least is the use of VPN over internet, or SD-WAN over internet lately. This one has been more predominant, and this is actually the one that a lot of organizations use today. Right, so let me update that, because the proponents of SD-WAN, although it is an evolution of virtual private networking, will get offended if they are called as similar to virtual private networking. So software-defined WAN is becoming popular as well. So just use regular internet connectivity like what you and me are using at home. And we're going to put the SD-WAN technology or VPN technology on top to provide more reliability. Right? And of course, in reality, voice and data are the same. You can either have a dedicated network. So in this case, wide area network, your phone is in a separate network and your wide area network is separate for data. Or in this case, you have your data part here and you have your phones that run on top of the data via voice over IP, which has become more popular. Okay, just as a recap, here's the signaling layers. I just put this here for reference in case, so that you don't have to go back to the previous slides, right? So when we say DS3, for example, that roughly means 45 megabits per second. Carrier system is actually T3, right? Or a DS0, T0, E0 is always 64 kilobits per second. And that's the reason why when you say a T1 circuit, that actually means 1.544 megabits per second. T3 circuit is 44.736, or roughly 45 megabits per second. Okay, so circuit size matters, and this is where you can look at it. And there's also the E series, which is used in the Philippines. You can buy an E1, which is the most common type of leased line, right? If you buy it from a telecommunications provider, and that will roughly give you 2 megabits per second. Okay, E3, for example, is roughly 34 megabits per second. So this is quite useful in conversing, especially when you're buying these lines or you're describing the size of a circuit. Right. And in terms of optical technology, the OC series, here you see OC1, which is roughly 52 megabits per second. OC3 is one of the most popular. It's 156 megabits per second. So you can actually subscribe to SDH circuits with OC3 size, which is actually the smallest SDH circuit. So that's why it's called SDH1, right? Of course, you know how the numbers work, right? So if you say SDH3, that's 3 times SDH1. Right, SDH4 is 4 times SDH1. So OC3 is 3 times OC1, and so on and so forth. Right, so that gives you a relative indicator of the size. So SDH1 or OC3 is the most common optical signal if you subscribe to a traditional telecommunications network and you buy something called a leased line. Okay, first off, wide area networks, and this still is very popular today, is SONET, right? So SONET is synchronous optical networks. It is only a physical layer standard, right? It's now standardized today as what we call synchronous digital hierarchy, or SDH, right? We talk about data rates in terms of optical carrier levels, or OC levels. And as the slide previously showed, OC3 or SDH1 is the smallest circuit you can buy with that uses SONET, right? So 156 megabits per second. This is what SONET equipment would look like. So basically, you have your optical links plugged here. You have controllers. This is our usually management in interfaces. This is a larger version of SONET equipment, right? And these are normally in the core backbone of your networks. When you tap into this in circuit, for example, you can tap into this, right? And these are where your client connections would come in, and these are the backbones for the backhaul. Let's now move on to some examples of copper networks. So the first one, the oldest one we're going to be discussing is ITU TX.25 or X.25 network. So X.25 was developed by the ITUT at that time. This is an old network. It was still called CCITT. Specifies how to maintain computer networks. It defines layer 1, 2, and 3. This is also the reason why X.25 is no longer very popular, because it defines layer 3, which is outside of IP. Kasi yung most popular network natin ngayon is IP. Therefore, most WAN technologies or LAN technologies therefore only cover layer 1 and 2. But X.25 being an older network and IP not being that popular at the time, defined layers 1, 2, and 3. That's the reason why it's no longer being used today, right? So it does what we call hop by hop flow control. So it does layer 2, layer 3 flow control. So it's aware of packets and can do flow control in the packet, providing a reliable connection. So it's the one that handles retransmits, duplicates, etc. So think of it like, again, TCP, but X.25 provides it. X.25 being a layer 1, 2, and 3 protocol defines all those layers. Therefore, it also provides the physical media, which in this case is copper. Defines the speed, 64 kilobits per second, which is your E0 or T0, okay? Right. Next one is SMDS, or Switch Multi-Megabit Data Service. This is just an attempt to upgrade, for example, X.25. So instead of just running at T0 speeds, you can run from T1 to T3 speeds, in this case, 1533, roughly 45 megabits per second. Though it does not provide error checking. There is always this debate on who does the error checking. You can let the network do the error checking, or you can let the application do the error checking. By allowing the application to do the error checking, you make the network simpler and therefore faster. But if you let the network do the checking, then checking can be done at the earlier part of the transmission instead of waiting for the entire transmission to get to its destination before it is checked, right? So there are pros and cons of each. And I think the world has moved to much simpler networks. Very basic error checking at the L2 level, and no more L3 error checking, unlike X.25 that did L3 error checking. And we let the application do the error checking instead. This assumes that both devices at the end are the ones that do the error checking themselves. Next one, the third technology we're going to discuss in the copper space is what we call frame relay, right? This one became popular for a long time. It's a simplified version of X.25, focuses mostly on packet switching, similar to X.25. However, removes the end-to-end hop by hop flow control. So you don't do flow control at every hop, you do flow control at the ends, right? This allowed you to make the network a lot simpler, therefore cheaper to implement, and therefore also faster. But in order to do reliability, that has to be checked at the end. Therefore, if the network is not reliable, performance would degrade very, very quickly, right? So control signals take place on separate logic connections. So the nodes don't need state tables to know each other, right? So it's basically managed by a frame relay network. Frame relay networks deployed by telecommunications company tend to be shared. So you connect, for example, branches to each other. If you want to connect, for example, your retail stores to each other, you don't have to connect a circuit from your main headquarters to every branch. Instead, you all connect to a frame relay network, and the frame relay network will switch. Think of it as a giant switch, the connection between all your branches, which makes it a lot cheaper and a lot more efficient to implement. So a traditional packet switch networking would look like this. For example, XAT25 would look like this. There's hop by hop flow control. At every step of the way you decode, you store, you check. Decode, you store, you check. Decode, you store, and guess its destination. As opposed to frame relay, you simply encode, route it, and decode. And the expectation is the checking is done at the nodes themselves, right? Simplifying operations. So definitely this is more, takes more performance and more activities than this. That's why XAT25 went out of favor. Frame relay became a lot more popular. And it at one point, it was also timely because frame relay was created or became popular during the time of the rollout of ATM machines. And so there's a lot of banks and financial institutions use frame relay networks to provide intra-branch or intra-ATM communications. These are the things that frame relay provided and made popular. So it has a concept called congestion control, right? Which XAT25 did not have. So the idea of congestion control is you are able to maintain a certain quality of service. Why is quality of service important for frame relays? Because it is a shared network. Being shared, you kind of have to make sure that everybody behaves in the network so that you can provide a fair amount of resources to those people in the network. And if there is a problem like congestion, it does not affect everybody, right? So this is why we need something called congestion control. Congestion control brings us to the next feature, which is basically traffic rate management. Because you have the ability to manage congestion, right? So you can discard frames, for example, for people who are trying to use too much of the network, then you can manage traffic. You can tell, or you can create guarantees. And this is where we find the terms committed information rate or CIR, which has become popular lately when discussing your broadband connection, because this is the rate of speed, the minimum rate of speed that your carrier will guarantee you will get all the time. So if I buy a circuit and they give me a CIR of 1 megabit per second, any time of the day, no matter how congested the network is, the network should be able to give me 1 megabit per second, right? And if I exceed it, for example, and I don't have any variable or what we call burst rate, then traffic is discarded beyond that, which is quite useful because it allows you to create rules in which people behave. So anything below CIR is guaranteed. Anything between CIR and the burst rate or your max rate, transmit if you have resources, and everything over the max rate is discarded. Therefore, when you subscribe to your broadband connection today and it says 50 megabits per second, 50 megabits per second is not the CIR. That's your max rate or that's your burst rate. So this is the 50 megabits per second. You can get anywhere between 50. If there is no CIR, which a lot of telecommunications provide no CIR, then it will only transmit if possible from 0 to your maximum rate. So from 0 to 50 megabits per second. But if you have a CIR that says 1 megabit per second, then if you need 1 megabits per second, it will always give you 1 megabit per second. But between 1 and 50 megabits per second, it will provide the service if available. So if you notice, because of frame relay, we are now introduced to the concept of traffic management. And this is how CIR, burst rate, or max rate works. And even up to today, even if networks are not frame relay anymore, we still use the term committed information rate. So I'll take a pause for a while to get some questions on frame relay, XAT25, SDS, and SONET. Are there any questions so far? So again, these networks are fairly straightforward. Of the 4 that I mentioned, only SONET still exists today, right? So the rest, I mean, they still exist, but they're not being sold anymore and they've been obsoleted, and maybe some grandfathering on frame relay still exists. However, even if frame relay is no longer popular, the term CIR or committed information rate is still being used up to today. So yun naman yung still popular up to this point because this technology introduces the terminology which we are still using up to today. And the evolution of frame relay was to create an even better frame relay. The better technology is what we call a synchronous transfer mode. Right. Synchronous transfer mode basically is an evolved version of frame relay. Again, it's simple. There's no hop by hop flow control. It only covers layer 1 and 2. That's why it's IP compatible. But instead of dealing with frames, it's dealing with cells. So it divides the frame into smaller cells that are not bits. Therefore, the smaller unit of measure allows you to transmit data in a more seamless fashion. So again, it is more streamlined than frame relay, even frame relay. Of course, much better than XM25. And definitely it supports data rates on the order of magnitude greater than frame relay. The reason being is ATM decoupled itself from the media, right? So ATM actually layers on top of networks like Sonnet, for example. That's why you can get Sonnet speeds and SDH, right? Which is the official ITU term for Sonnet. So for Sonnet networks, you can get really, really high amounts of speed, and you layer ATM on top of Sonnet. Therefore, you can get higher rates of speed when you use ATM, right? So again, they're broken down to cells instead of fixed sized packets, right? There's no link by link flow control as well. It's similar to frame relay. What happens is it's not on the end connections, right? You don't check at every step of the way. You're expected to check at the ends. It is identified with telephone lines because you can layer telephone PSTN on top of ATM networks, okay? And the nice thing, okay, this is the thing that ATM networks introduced, is the concept of a virtual channel and a virtual path. Unlike frame relay, where you can give people CIRs and burst rates, which is pretty good at the time compared to the XL25, you can't, it is still predominantly a packet switch network. You can't really do, it's challenging to do things like voice on an old frame relay network, especially frame relay sizes, which is only like T1 size, 1.544 megabits per second. It was quite challenging to do lots of things in frame relay network. But in ATM, it created the concept of a virtual channel and a virtual path, which allows you to bundle a set of channels in the case of virtual path, and each channel will have a dedicated amount of bandwidth allocated to it for that entire period. Therefore, you can simulate something called a virtual circuit, which we discussed last meeting. So ATM is the realization of that, right? Your physical path can be broken into many virtual paths and broken into many channels, and you can give channels to specific endpoints in your ATM network so that they can treat those channels as if they were dedicated circuits, right? Virtual circuits, okay? Advantage of virtual circuits is you can treat them like a dedicated circuits. For example, is a leased line, right? So you can say, oh, leased line from point A to point B, and I have 50 megabits per second. Then at least it's guaranteed to you. Simplifies the architecture, performance is improved, and of course, setup time is shorter because there's no high load. That path is dedicated to you. So it allows you to simulate many kinds of virtual circuits, right? And of course, since it is a virtual circuit, right, it provides you a certain degree of quality of service. It is permanent, right, or can be permanent, so you can switch it on and off. But when it's on, it's permanent for you, right? Cell sequence integrity, flow control is provided for you in the case of a virtual path and channel. So you can choose. If you use a virtual channel, then it provides guarantees. If you don't use a virtual channel or you pure packet switching mode, there are no guarantees, but performance is better. That puts it in the hands of the administrator to determine how best to use that capacity. ATM has evolved, right? So frame relay traffic management. So this is what traffic management in ATM looks like. You have what is called real-time enforcement. So this is enforcement that's done in real time. And if you notice, it is similar, if not the same, as frame relay. Your CIR, or constant information rate, is now constant bit rate, or CBR, right? This is similar to your ATM frame relay CIR. And you have what is called real-time variable bit rate, or RTVBR, which is effectively your burst rate. Now, in ATM, the difference between ATM and frame relay is the VBR, or the burst rate, can be variable, right? And anything between this VBR and CBR would be best effort, and anything below CIR or CBR should be guaranteed. Now, there are non-real-time enforcements such as non-real-time variable bitrate that can be given to you if more capacity exists. So you have a lot more flexibility. Instead of a fixed VBR that says 50 megabits per second, you can do a non-variable portion, right? A non-real-time portion that adjusts. Then that can provide you more capacity in the case of non-real-time. So that's why this thing moves, because the rates may be available or not available. right? And there's terminology also such as available bitrate and unspecified bitrate. Unspecified bitrate is you can use as much capacity as you like, but only when available. So it provides you more classes of traffic management outside of the traditional CBR burst rate. Now you have CBR, RT-VBR if you want to simulate frame relay, or you can have an NT or non-real-time VBR that can move, right? Or you can give them an available bitrate, which is like a fixed rate, or you can give them no bitrate, right? It means no guarantees, but you can use whatever you need. Okay. Question so far on AETM. So the major benefit is, of course, you can do real time because again, you can provide these guarantees and you can create a virtual channel. You know, those are the elements that kind of allow you to simulate the circuit switch network. There's minimum variation, so there's not quite a lot of delay, especially when you're using circuit virtual channels. And that's the reason why you see ATM networks, especially in the late 90s and early 2000s, become quite popular in creating what we call quadruple plays, right? So you actually can run data, voice, and TV in the same circuit. Now, of course, we run data, voice, and TV in the same circuit now, but we use a different type of technology. All right, so these are just descriptions of the other bit rates. I'll skip them for now. And let's move on to the next technology, or broadband ISDN, which is basically a combination of ATM over SONET circuits. So this is what we call it today, broadband ISDN. So when you say ISDN services from a telco, you're technically getting an ATM service over SONET or SDH circuits, right? And that's the reason why, since it's over SDH circuits, your smallest speed, which is SDH1, is 155 megabits per second. At the time of writing of these slides, which is quite a while ago, you can get up to 622 megabits per second. Now, nobody really buys that amount of speed yet nowadays, but you know, it is available in case you need it, right? So you can go all the way up to gigabit speed with broadband ISDN, right? So broadband ISDN is simply ATM over SONET. You use SONET at the bottom, at the layer 1, ATM at the layer 2, right? Well, SONET at layer 1 and part of 2, and ATM at the upper part of layer 2, and IP and friends at layer 3 and above. Okay, so in summary, these are your WAN choices. These are your what they call legacy WAN choices. Now, I'm not talking about the new technologies yet. These are the ones that have been available for a while, right? So up to the year like the 2000, these were the technologies that were common. So you would see, for example, in terms of analog technology, this is your dial-up, right? The dial-up can be anywhere between 4.8 kilobits per second to 56. Dial-up is always normally 56. So whether it's a shared network, which is switch, or a non-shared network, it's really up to 56 kilobits per second. However, you can buy a lease line, right? So non-switch, again, it's dedicated to you. It will be 1.54 megabits per second. Although we're in the Philippines, so you'll probably get a P1 circuit, which is 2 megabits per second. And you get frame relay, which is generally between T1 and T3, or E1 and E3. So in case of E1 and E3, that will generally be 2 megabits per second to 34 megabits per second. And a DS3 or an E3 would probably be 34 megabits per second. So you can order that. I want a frame relay circuit, but I want it between 2 points. That's the benefit of frame relay. You can buy it in leased line mode or leased mode or switch mode. So it's a choice. But T1 circuits, dedicated T1, T3 circuits, or dial-up circuits, well, T1, T3 circuits are definitely point-to-point for these lines. Then SONET, right? The old SONET can be up to OC1 and higher, but the ITU-T version, which is SDH, is 155 megabits per second, or SDH1, which is OC3 and up. Right? So it can be up, and right now there's no, there are quite large limits to that. I think we've gotten it up to like terabit per second already in a single circuit. Now, for switch means you connect to a switch network, right? Or a cloud or frame relay network. So in this case, you can dial up, and still you can dial up into a switch network. The switch network allows you to access to other networks. X25 is the same thing, right? It allows you to connect to a packet switching networks or shared switch networks, which is also true for ISDN, but these are the speeds, so 64 to T1 speeds, right? DSL is generally between 16 kilobits per second to 9, but we've seen 9 megabits per second, but we've seen DSL speeds increase in the past year. And we will have a separate lecture actually for DSL and its developments, right? Because it is still very popular today. But I added DSL here so that you can see and compare between the technologies that we have been discussing, right? So regular ISDN is very small. If you notice, it's only from E0, T0 to T1, right? But with broadband ISDN and you run it with ATM over SONET, then you can do up to SONET speeds and it's a switch network as well. So this one might be just here, right? But BISDN can be from 155 to, whatever limit we have today. In this case, it's 2 terabytes. Okay. Questions so far on WAN choices. So when we make selections, we normally look at this table, all these selections in the 90s, right? So this is normally what you had. If you took a time machine and you moved yourself to the late 90s and early 2000s, these were the choices you had, right? Which is quite great because you still have broadband ISDN, right? Allows you to have an ATM style interface and guarantees, but it provides you a amount of capacity driven by developments in SONET technology, which still continue to be developed up to today. In the early 2000s, you could probably still get frame relay, but it would be limited with 65 kilobits per second to about T1 speeds, right? And you could still get legacy ATM. You can still buy the T1, T0, T3 circuits directly. This is the thing about the Philippines. We use the E-series circuit, so you'll probably get the T1, which is 2 megabits per circuit second, and a T3, DS3, which is 34 megabits per second. But since we have a lot of business in, say, the United States, you can actually get T circuits here also. You can get a T1 and a T3 circuit here as well, right? So it gives you that flexibility within the Philippines, right? You can't procure an SA25, an SMDS, or an older SONET network anymore. BISDN is still available and regular ISDN. Frame relay, I think, still exists, but it's no longer being sold. Normally, it was historically used for bank branches and ATM machines. Now, in summary, you can basically see that there have been developments as well. The ones I showed you are traditional WAN technologies, and BISDN being the most popular can provide you a large amount of speed. However, we are also seeing in real life today, wide area networking technologies being supplanted by local area network technologies. So for example, your GPON or your fiber to the home, right? So that's not FTTH, that's FTTH. So that's fiber to the home has already moved to GPON, right? So GPON or gigabit passive optical network are the fiber networks you have at home, right? So if you're Red Fiber, for example, or PLDT or Globe Fiber or Converge, you would be using GPON technology. Metro Ethernet technology has also become popular. Instead of buying a BISDN circuits at one, like a SDH1 or SDH2 in size, you can actually buy 100 Mbps connections, 200 Mbps connections via what we call Metro Ethernet. So this is the use of gigabit Ethernet or faster, which we'll be discussing in that local area networking technologies next week, as the basis for this. So you have your choice between LAN and WAN technologies. When you use WAN technologies, because you're seeing the pervasiveness of these types of technologies into the wide area networking space. So in addition to what you see here in the wide area network technology, with this being the most BISDN being the most pervasive kind, and this number can be bigger because SONET is still evolving. We are seeing this happening. LAN technologies being used at the wide area network basis. And the next trend is basically the use of technologies such as VPN and SD-WAN on regular internet connectivity. So your GPON connection from your retail provider, put SD-WAN on top or VPN on top. You can get the same guarantees as a lease line or a wide area network circuit, but it will be much cheaper and in some cases much more reliable. Right? So you're seeing that we're seeing these two trends, and these are the most predominant trends in the industry today. So your traditional wide area network technology will still be there, or you can get supplanted LAN area technology, or you can use VPN or SD-WAN on top of wide internet access today. Okay, do we have any questions so far? on WAN technology. So this is summary of WAN technology. So let's go through some examples so that at least we'll give some scenarios. So the first one is a hamburger chain, right, with branches nationwide that need to send sales information daily to a centralized sales tracking system, right? That is the only need. Let's just assume that it is the only need for networking for that particular hamburger chain. So think about this. You're in the Philippines. You're talking to a McDonald's or a Jollibee. How best would you connect the branches together, right? So obviously you need wide area network technologies because these branches are all over the country. Now, what wide area networking technology do you use? Okay, question number one. Do you use dial-up, right? You could connect telephones in all the branches and they dial up to the server, say in Jollibee Center in Pasig. Okay, that's one way of doing it. That would be the old way of doing it. So you dial up to Pasig, and Pasig would have this bank of telephones or bank of phone lines connected to servers that would take in these calls so that you can get the orders or the sales information from every branch. Possible, but not very practical. That would be a lot of phone lines, right? If you have 1,000 branches, then if they all connect at roughly the same time, you'll have to have 1,000 phones also at the headquarters. So not very practical if you're not using a switched approach. So definitely hamburger chain would benefit from a switched approach. So next is, can I do frame relay? Well, it doesn't exist anymore, but hypothetically, if frame relay existed, this would be a perfect use case. Why? It doesn't need a lot of bandwidth. Sales information is small, right? And it doesn't need the bandwidth to be available all the time. So frame relay allows you to cut a deal with the telecom providers to make it a lot cheaper. And so hamburger chain could definitely do frame relay system, but unfortunately it doesn't. So now I move on to the next technology. So in the Philippines, you'll have a choice of BISDN or SDH, right? Which I think is overkill. You don't want to give SDH1 or 155 megabits per second per branch just for sales tracking information. You probably want to use a cheaper technology, which leaves you with two choices, GPON or Metro E, right? Now, you'll probably use Metro E in locations where Metro E exists, or you would use GPON in locations where GPON exists. And they are all viable, right? And they're all switched, so you can connect your headquarters to the gigabit GPON provider's cloud, and you can connect the branches via GPON to the GPON provider's cloud. And you can use a mix and match. Some can be Gig E, some can be GPON, depending on availability. So that's one viable solution. It's more reliable. The telco will dedicate the service. But again, it's just a hamburger chain, and you don't really need a lot of bandwidth, and it doesn't have to be super reliable because you just have to send information once a day. So the option for this would normally could be VPN or SD-WAN over the internet. Or just get your retail fiber connection or DSL connection or even mobile connection and just run VPN and SD-WAN on top. So for hamburger chain, I'd probably do that because I don't really need a lot of bandwidth. I don't really need it all the time. It can even just be a mobile connection, right? Mobile connection, and with VPN or SD-WAN on top of it. The normal reason why you need some technology like VPN is because you need to be providing security, right? These networks, the internet networks, GPON networks, do not provide the security. Okay, option number two, or sorry, scenario number two, a bank with 100 or hundreds of ATM machines nationwide doing real-time transactions. Oh, this is different from hamburger chain because in hamburger chain, connections don't have to be real time. You just have to connect once a day to send information. So that's actually quite small amount of information. It's actually fast. However, banks have to have reliable connectivity. So can I use, of course, you can use BISDN, of course, just be expensive. Definitely you can use frame relay because the bandwidth is not too high. But would you go with BISDN and put 155 megabits per second per branch? No, it's too big. Even with GPON or Gig E, if GPON exists in that area as retail connectivity, that would be great. But most ATM machines are not even in locations that have broadband. So what would normally be used in these scenarios would be mobile connections, right? Smart Globe, Dito, and you could probably use SD-WAN to aggregate those connections to make them more reliable. So this is a scenario where SD-WAN over regular internet definitely makes sense. And the third is a call center that needs to terminate calls to the United States, right? operative word is United States that uses the TS series. Therefore, we need a DS3's worth of data. So that means you have to create a circuit, and this is where you need a DS3 or a T3 circuit from a telecommunications company. So this is fairly straightforward. You need a T3 circuit because you need to connect to a telephone company in the US to terminate T3 circuits worth of calls. Fortunately for us today, call centers are no longer designed like that. Call centers no longer terminate calls with traditional, signaling mechanisms. So what happens is most modern call centers today would actually be using regular internet connection and voice over IP. So again, VPN SD-WAN over internet makes sense in the scenarios you have. And last but not the least, enterprise with internet requirements of around 200 megabits per second. Obviously, your smaller connections like dial-up frame relay or even these lines, for example, up to T3 or DS3, don't make sense for this customer. So 200 megabits per second is within the realm of Metro Ethernet, for example. You can also do via ISDN for that. But Metro Ethernet tends to be cheaper in the Philippines. Therefore, most people with this requirement would probably be using Metro Ethernet or even GPON. You can get this at GPON. And with more advanced DSL connections, which we'll be discussing in a later lecture, this is now obviously available as well. Okay, so those are just examples of scenarios where you use different types of wide area network technology for different use cases. So that is it for today. So we will be discussing local area networking technology next week. Apologies, it's a bit noisy here, but at least we can start with that. And if you have any questions, just let me know, or you can send me some input in the chat. Please take note, there will also be a quiz next meeting at the usual time, and I will see you at the usual time as well. Okay, but before I go, are there any last minute questions or clarifications? Going once, going twice.